With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello students, our question is a particle of negative charge of magnitude q is revolving with a constant speed v in the circle and radius r as shown in the figure. Okay, so we have to find the magnetic field, magnitude and direction at the following points. The first one is center of the circle and the second one is a point on the axis which is at a distance x from the center of the ring. Okay, here we have to find the magnitude only and we have to predict that the action is constant all the time or not. So let us start. Where the charge is moving in anti-clockwise sense, and it is given that the charge is negative, so the current associated in the loop due to the motion of this charge will be what? It will be opposite to the motion of the charge, so current can be taken as clockwise. Okay. Now we have to find the value of current in the loop. So the time taken by the charge to complete one revolution will be what? It will be 2 pi r, that is circumference of the loop, upon the speed of the charge in the looping the loop. Okay, so it will be 2 pi r upon b. This is the time period of one revolution. Now the current associated can be understood as, let's say a charge q is moving in time t in the complete loop. Suppose here if we assume a cross section, so in one time period the q charge passes through the cross section. Okay, so the current associated in the loop will be equal to the average current, we can say as q upon t. Here we know the value of time period, so we can put it as 2 pi r upon b. So current can be written as I is equal to qv upon 2 pi r. This is current associated in the loop due to the revolution of charge. Okay, and we know current is clockwise because the charge is negative and it is moving anti-clockwise sense. Now we have to find the magnetic field, first one at the center of the loop. Okay, so let us draw the figure first. Let's say this is our loop. We have calculated the value of current in the loop and it is in the sense of clockwise. So at the center the magnetic induction is given by the formula we know, mu naught I upon 2 times radius of the loop. This is the formula for the magnetic induction at the center of a current carrying loop. Okay, and for the direction we can simply use the screw rule. Suppose we are pinning a screw which is perpendicular to the plane of the loop, and if we rotate the screw in the sense of direction of current, so here the direction of current is clockwise, so if we will rotate the screw which is pinned at the center, so it will move inward. Okay, so the same will be the direction of the magnetic field, where the magnetic field will be in cross direction, that is going inside to the plane of the loop. Now we can just substitute the value of current in the above expression to find the final expression for the magnetic field. So magnetic field at the center can be given as mu naught I upon 2r. So I can be written as qb upon 2 pi r. So it is coming to be b at center is equal to mu naught, sorry, it is mu naught into q into b upon 2 pi r square. Sorry, it is 4 pi r square, right? So this is the final expression for the magnetic induction at the center of the loop, and for its direction it is inward, so we can write it as cross. Okay, now we have to find the magnetic induction at a point which is x distance away from the center of the loop on the axis. Okay, so let us draw. on its axis. So let us draw the diagram first. Suppose this is our loop and this is its axis on which we have to find the magnetic field. So there is a point P which is at a distance x from the center of this current carrying loop. We can say, okay, it is at distance x. Here the current is also in the clockwise sense, so it will be this way. So here we know the formula. On the axis of a current carrying loop, the magnetic induction at a point on its axis is given by mu naught I radius square upon 2 into radius square plus distance from the center whole power 3 by 2. Okay, and we also uses the same concept of a skew rule here. So we can now just substitute the value of current in the formula to find the magnetic induction at the axis. So B axis can be given as mu naught. We can just substitute the value of I. It is QB upon 2 pi r, right? So QB upon 2 pi r. This is our I. So mu naught I into r square upon 2 into r square plus x square raised to the power 3 by 2. So we can now just simplify this. See here r square, the square term of r square is cancelling. So we can write it as mu naught QBR, mu naught QBR upon, in the denominator it will be 4 pi into x square plus r square power 3 by 2. Okay, so this is our final expression. We can rewrite it as B axis is equal to mu naught QBR upon 4 pi times x square plus r square whole raised to the power 3 by 2. Okay, so this is the final expression for the magnetic induction at a point on its axis. We can now see for the direction. Okay, so this is the final expression for the magnetic induction at a point on its axis. Now look for the direction. Here the magnitude is, you can say, if the point is fixed, so magnitude is fixed. Now looking for the direction, as the current is in the same direction, that is in clockwise sense, so direction of the magnetic field at this point will be simply just spin screw here also and rotate it in sense of current, so it will again moving inward, that is towards the loop. So it will be the direction of magnetic field here, and since the current in the loop is constant, also the direction of current is constant, so magnetic field vector at this point will be constant. So look for the question. Here it is asked that is the direction constant all the times. So we can say yes, direction is constant because the current in the loop is constant, that is in clockwise sense, so direction will also constant. So I hope you are clearly able to understand both the parts of the problem. Okay, thank you for watching.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.